Welcome to radar system course. Today we will learn a radar receiver. What is the role of a receiver or what is the function of a receiver? Generally, a receiver is detecting that radar receiver is used to detect a echo signal. That echo signal reflected from the target or it will come from the target, and that signal reaches to the receiver. That will be detected by the receiver, and that signal whichever reach or whichever come at a receiver, it consists of a noise or it consists of a clutter. So that's why at a receiver we are getting a two types of a signal. One is about a desired signal and another is about a noise here. So now we are interested in a desired signal. We need to suppress the noise. So that noise consists of various types of a signal frequency. So we can suppress through the filter or we can suppress through a technique in which we use a threshold and all so that we can suppress the noise. Because whichever the echo signals we are receiving, it has some level, and a noise may have a small level of a signal. In that case, we can consider a threshold value, and above that particular threshold, signal is to be considered as a desired signal. But above that threshold, if some signal is there, that signal consists of a clutter. So in that case, so there will be a false understanding by the receiver there. Okay, or we can say that a false prediction. So even if there is no target, but receiver is recognized something is there, so that's why it's called as a false prediction or false probability of receiver. We need to find out what will be the false probability of receiver. So that echo signal received, that may be the desired as well as the unwanted one. So we need to separate out or we need to remove whichever the unwanted signal before amplify. Okay, because in a radar receiver, one more block is there. It consists of an amplifier because the signal level is very low for the display devices. So that's why we need to amplify the signal level so that whichever the desired signal is there, so we need to use a amplifier there. Once we are using a amplifier, so that we can provide the signal to the a display device. So what are the various display devices? So there is some CRT tubes. So color tubes are, we can say that a gray scale or a gray value can be seen, gray images can be seen on the display devices. So in general we say that it is about a CRT, that is about a cathode ray tube. But in terms of a radar receiver that displays, they have the various types. So that's why we can say that the displays have a types, whether it will display only the amplitude or present whichever the target is present, or whether it will produce or whether it will display the noise part, whether it will produce or display the range as well as the azimuth and elevation angle, everything. So according to that, there are various types of a display. Then displays based on the what type of a tubes we are using, okay, whether it will be a color or a black and white only. So according to that, we have a cathode ray tube. Nowadays, lot of displays are used for displaying the device. So whichever the signal received, that will be a desired signal. An unwanted signal is to be separate out before amplifying the signal. If supposed to be unwanted signal amplified by amplifier, then we are not able to recognize or we are not able to identify whether that signal, whether the signal belongs to a desired one or belongs to a noise. So that's why we need to separate out whichever the a noise in the signal there. So designer is to consider here what will be the frequency for the signal here, and as well as we need to consider that what will be the a threshold level. So here a part of unwanted signal, and this one is a desired signal. And the desired signal consists of a target information in terms of a range, in terms of a azimuth and a elevation angle. And that information that will be given to the display devices. So display devices consist of a processor, and then that data is to be processed, and according to that it will be displayed on the display devices in terms of a range or in terms of a azimuth and a elevation there. Then we need to know about what type of a receiver we need to use it, because if you consider at a radar receiver, so we can consider that there will be some sort of a device, we can consider that a mixer, and we are supposed to use a local oscillator, and then after that we have a IF, okay, and then we need to use a display devices or a processor there that will be used to display the content. Okay, just like this one is about a display device. But now a signal, incoming signal, reaches at the input end or a front end of a receiver through the antenna. So noise enters from the antenna as well as the noise present in each and every device or a component. There will be the noise from the local oscillator, mixer, IF. There will be the noise for the IF also. So various components are there. So total noise, if you consider for the radar receiver, that consists of a noise from the unwanted signal, or we can say that at the front end of the receiver, because front end is nothing but the antenna, and a noise from the network component or circuit component. So while designing the receiver, we need to take care of what sort of a component we need to use so that noise can be minimized. So our aim here to improve the signal to noise ratio. If our signal to noise ratio improves at the input side as well as for the output side, so we can consider here a figure of merit or a noise figure will be improved. For a specific receiver, so what will be the noise figure? Okay, that is to be considered. So that noise consists of interference from the nearby devices, then a clutter echoes, or we can say that from the natural element, so noise came in the particular receiver. Okay, but generally what happens? Radar receiver used at a higher frequencies, so the nearby devices, those working at a low frequencies, they does not affect to the receiver. There is no issue from the low frequency devices, but the devices those are operated at a micro frequencies, they may create a problem at a receiver. That can be considered as a noise. So in general, because the radar receiver operate at a micro frequencies, so that's why there is a low devices present in the given particular frequency range. So that's why the noise from those devices will be low here. But only the noise from the nearby devices, that is about nearby radar devices or a nearby target or a clutter likewise, that part is a low now. But another part of a receiver, that is part from the noise generated internally within the receiver. Internally generated receiver noise means what? From the mixer, from the local oscillator, from the intermediate frequency, from the display device. Okay, so likewise. So there is a noise present from the external as well as the internal. Now we need to design a receiver so that it will provide a maximum signal to noise ratio. That value will be a maximum. So for the maximum signal to noise ratio, we need to suppress the noise so that a signal to noise ratio will be increased. So how to increase the signal to noise ratio? We need to consider a match filter so that a signal to noise ratio will be improved. And then we need to use a device. Here we have a junction, that is a T is to be used because it is a duplexer here. Because antenna, if you consider, the same antenna is useful for the transmitting purpose as well as for the receiving purpose. So that's why here is some switch. The noise will be at switch, mixer, or every device with it. So we need to proper matching those particular components or proper use of those components, so that will reduce the noise state. Once we receive the signal, the signal consists of a external noise, okay, that can be removed from the this component. Then for each and every component, signal pass through. So maybe because of that internal noise generated at this particular component, so noise again present through this particular component. So we need to separate those noise from the external as well as from the internal one, so that your receiver will provide a higher signal to noise ratio then. So what will be the total gain of the receiver, or we can say that amplifier we are using in a display devices, okay, or you can say that there is a mixer, for the mixer some gain is there, okay, likewise. So for each and every component some values are there, okay, in terms of a signal in and signal out. So that will be used to suppress the noise. So we need to find out for a given particular receiver, so what will be the exactly a gain of a component, so that a signal to noise ratio will be increased. So while designing the receiver, so we need to see a few factors. So in that case, we need to know about what will be the gain, then what will be the phase, then we need to know about what will be the stability of the component. If you consider the amplifier there, then in terms of a amplitude stability here, and then your devices work in a what frequency range, we can say that a dynamic frequency range, so that we can use a match filter there. Then a tuning at what particular frequencies, and then whatever the devices we are using, they are a resonance here. So these are about the component while designing a receiver. Along with that, we need to consider that a protection for each and every component against a overload or a saturation or a burnout from the nearby transmitter, because a transmitter generate a high power signal. That higher signal, a power signal, could not reach to the receiver, otherwise receiver will damage. So device receiver has to on and off for a particular conditions only, or you can say that the transmitter is to be on and off for a particular period of a time. So what will be the transmitting time of a pulse required, and then after that we need to use the device for the receiver. So we need to switch on and switch off a transmitter as well as a receiver. So switching time or the explosive. So we need to use a device so that a transmitted signal not propagating through the receiver component. Otherwise, the receiver will damage. So that's why we say that burnout from the nearby transmitters, and we need to find out at what particular time that transmitter is to be on and off. So that so we use a switch here, or we can use a duplexer or a circulator, so that the transmitter at a time of a transmitter signal will not reach to the receiver, or at a time of a receiver signal not reach to the transmitter, because high pulse signal generated from the transmitter that will damage the receiver. So that's why we need to use a switch here. And a receiver is nothing but a super heterodyne type. So for a super heterodyne type receiver, so we can consider a local oscillator and a mixer. So that local oscillator we are using in the receiver. So that local oscillator, it consists of a crystal, and that crystal is to be a stable one for a given particular frequency range. So operating frequency range of a receiver, we need to know at what particular frequency crystal will be stable there. Okay, even if we say that a crystal is stable, in general we say that statement crystal is stable, but again it will generate some particular noise within a particular range of a frequency there. Now we see here what are the various components that will affect the receiver. We can say that we need to improve the signal to noise ratio. So that's why we need to remove the noise. This we can say that is unwanted signal. And that unwanted signal from what? Whether it will be external at, you can say that at front end of a receiver, okay, or we can say that at a antenna, and we can say that a signal from the internal one, internal component mixer, local oscillator, duplexer. Okay, likewise. So we can consider that is about a noise now. So for a noise removal, we can choose a appropriate component at front end as well as for this particular internal, and we can try to remove the a noise, or we can try to suppress the noise there. So for a device or for a system, what will be the a noise figure? So noise figure of a receiver, that is nothing but measure of a noise produced by the receiver component, or we can say that a noise figure Fn is equal to whatever the noise generated from the available input. Okay, so noise, that is a signal available, input signal and available noise input here, divided by available output signal power as well as the output noise power. So in general, if you solve it, we can say that S in is nothing but a signal available and a S out. Okay, so if I consider this one, it will be what? S out and S in. And the factor is to consider that power signal power, output and input ratio, that is nothing but a available gain. So we can say that S out by S in is equal to available gain. And this input noise, it will be depending upon the Boltzmann constant, what will be the available temperature, and what will be the noise bandwidth. So we can rewrite this equation instead of a S in N out here. So we can say that N out will be what? That is about the output noise available divided by S out by S in, that is about a G, here K, T, and a Bn. In general, we can say that is about a T0, that is about a available temperature at a 290 degree Kelvin. Okay, now we can consider Fn is equal to N out. That will be the output noise from the device. We can say that this one is about a component. We can say that receiver here is your N out now. For this particular N out, so that N out consists of what? Overall noise of this particular system plus whatever the noise generated internally. So that's why we can rewrite this noise figure, that is a KT0 Bn into G here plus delta N, and this one is KT0 Bn G. Okay, this one. So if we solve it, so we'll get that 1 plus delta N divided by KT0 Bn G. Okay, that is about it noise. And this noise delta N is nothing but a noise produced or noise present or introduced by this internal component, or it will be generated internally. So this is nothing but a noise figure. Fn is a noise figure. So generally a noise figure can be expressed in terms of a noise factor also, or we can write a noise figure in terms of a decibel there. So that is about a 10 log of Fn, we will get that a noise figure there. While defining the noise figure, we need to consider that input and output of the device is to be matched. So sometimes for array matching conditions, signal to noise ratio will be improved. Sometimes for a mismatch condition, a signal to noise ratio will be improved. So that is about a conditions for the matching as well as the mismatching at some particular mismatch only. So less noise will be obtained. So that's why we need to achieve the signal to noise ratio. We can consider the different conditions and we use the different devices so that a signal to noise ratio will be improved. So now we see that a noise figure for the cascaded network, if we have a two networks in a cascade, one we can say that F1 G1 BN. Okay, so F1 G1 BN, then F2 G2 BN. Now these are the two networks cascaded here. So what will be the noise figure here for these two devices? So first we can consider that it has a noise figure f1 and a gain g1, but the bandwidth is same for these two devices. So available bandwidth bn here, that will be the same. Only that f1 and f and g will be different for this different component. So our aim is to find out what will be the overall noise figure of these two circuits in a cascade here. So the output here at this particular device, so we are getting the overall noise. So we can say that this one is about the output. So n0 is nothing but the output noise of these two circuits in cascade here. So n0 is equal to what? It will be nothing but a noise figure f0, that is about the overall noise figure f0, and then again g1 g2 of devices, then again d0 and a bn. So if we simplify it, so this consists of what? A noise from the network 1 at the output of network 2, and then a noise introduced by this, and so then we will get the total noise by the network here. So we can consider a total noise that n0 is equal to what? A kt0 bn f1 g1 g2, that will be noise from the network 1 at the output of network 2, plus what will be the noise introduced by this factor. Okay, so we can say that is dn2, that is internally one, okay, internal generated by the network 2. So we can consider this case, and then we can solve it, that dn2 is nothing but what? It will be a noise introduced by the network 2, so that by f2, okay, that is the noise figure will be the f2 here. So we can write a k0 bn f1 g1 g2 plus, that will be the noise figure produced by the device 2, so that by f2 minus 1 into kt0 bn g2, and then we can write this one is the n0. So in terms of noise figure, so if we are writing, so we can write here a f0 is equal to what? f1 plus f2 minus 1 by g. Okay, so we are getting the f0 because a n out, what will be the n0 here, divided by the kt0b. Okay, f0 is equal to what? Already we have seen that f0 is equal to kt0. So we will get the f1 here, and here we are getting the term g1 here. Okay, so g2 get cancelled. So we have a g1 g2 for this divide. So we have this particular term. Since there are the two components, two networks are in a cascade, so that's why there are the two terms. So if there will be the n cascaded network, so in that case f0 is equal to what? f1 plus f2 minus 1 by g1. Okay, then f3 minus 1 g1 g2 plus Fn minus 1 G1 G2 Gn minus 1. Okay, so now this will be the equations we have obtained from the noise figure. If we have a n networks in a cascaded, n network in a cascaded here, so this will be the noise figure of a n network in a cascaded. But in the expression, if you see here, so we have considered that Bn will be a constant noise bandwidth, same because bandwidth not affected, and again we have considered that the temperature, okay, that's about for each and every device it is to consider same here. Okay, ambient temperature here. If we consider the network for each and every cascade network, the temperature of the individual network will not be the same. The components are different, so that's why there will be the difference in the temperature for the device 1 and device 2. That's why if we consider that a T here for the temperature, then while we cascading this particular network, so overall noise temperature by this network will be a different. So noise introduced by each and every network, each and every network, so that a overall noise is nothing but the effective noise temperature, and we can define that effective noise temperature in terms of a noise temperature at the input of the network that will create a noise, or that will be a part of a noise at the output. What will be the temperature here? So for example, for this particular element, there will be supposed to be T1 now. So that at a n out, when we calculate the noise at this particular network, so that noise, while calculating the noise, the temperature of this particular network will be considered. So in that case, here we consider that a Dn, that is a noise introduced by the network, and that noise introduced by the network, it consists of a temperature for this particular network. So we find out what will be the effective noise temperature in terms of a noise figure. So already we have seen that a noise figure, we say that Fn is equal to, we say that 1 plus delta n by k T0 Bn, and now this is about it a noise. So this Dn, that is a noise introduced by network, and that noise introduced by the network, which consists of a noise due to the temperature at the input of a network. So that's why this particular factor can be replaced with the effective temperature, and then we can rewrite this expression, okay, whatever the above expression we say, that can be rewrite with respect to the effective temperature, and that effective temperature we can write here 1 plus Te by T0. This is called as the effective noise temperature. Ta is nothing but a effective noise temperature, because we say that delta n is equal to this one is equal to K T E B N and C. So this K cancel, T cancel. So that's why we will get a Fn is equal to 1 plus T by T0. Or we can write in terms of a Te is equal to Fn minus 1 into T0. So in general, so effective noise temperature of the given particular network means for a cascaded network, these are the cascade 1. So every network has a 1, 2, they are in cascade. So it has the effective noise temperature. But overall system noise temperature, when we are calculating, so that overall system noise temperature is depending upon the effective noise temperature of the each and every block of the receiver as well as the effects of the antenna temperature. Okay, so we can consider that we can write a system noise temperature is equal to, we can say that a TS. The TS is consist of what? The effective noise temperature of a device here plus what will be the temperature of a antenna. Okay, we can say that noise temperature of the effects by this antenna temperature. So this one is called as a system noise temperature. So it consists of what will be the noise temperature, effective noise temperature of the receiver's system component as well as the effects of the antenna temperature, that is about a TV. So this system temperature, system noise temperature, it is again called as a operating noise temperature of the system there. So this will gives us the TS is nothing but what? A effective noise temperature of the system. It consists of what? A effective noise temperature of the receiver. It includes the whatever the components we have as well as the receiver component here as well as the component from the antenna there, noise temperature from the antenna. Or we can say that overall in terms of a noise figure, so we can write a T0 to a Fs. Here the Fs is nothing but what? A system noise figure. This one is about a system noise figure that include the effect of the antenna temperature. Okay, this is about a system noise figure. So we have written earlier a noise figure for the cascaded network. If we have a n number of networks present, so we can rewrite, okay, that a effective noise temperature of the receiver, that is TE, is equal to T1 plus whatever the component we have, how many components we have, T3 by G1, G2, like that. So that we will get the effective noise temperature there. Okay, of the system component. You consider that this one we have the n network or how many number of networks we have. Okay, that networks are in a cascade or a component or in a cascade. So for a given particular receiver, we need to know about what will be the noise figure as well as the effective noise temperature, and we need to measure the noise figure of the radar receiver in terms of a effective noise temperature. So at a receiver, which components we are using, because devices, solid state devices we are using at a receiver. So that solid state device here. So what will be the noise temperature of this each and every component in the receiver? That will provide you the effective noise temperature, and that will give us the noise figure of the receiver. So Fn. So generally we can say that in noise figure we can refer, earlier we say that Fn is equal to 1 plus effective noise temperature by T0 here. So we can refer that Fn, and we can find out what will be the effective noise temperature of a system, because we have a different component there, so we can find out the effective noise temperature and we'll get the a noise figure. So any of the device we are using, okay, whatever the network components we have present in the receiver. So first component that will the straight away gives you, so whatever the noise temperature generated by this device, that will consist of the effective temperature, right? So we can degrade this T2 by increasing the G1, so by increasing the G2 likewise. So with this component away from this, okay, first whichever the first component in a receiver, so that first component that will consider as the effective noise temperature. Okay, so first component their noise temperature T1, second component their noise temperature T2, but that effect of that noise temperature T2 can be minimized or reduced by increasing the gain of the device of the first thing. So whichever the first device we have, we need to increase the gain of the first device so that this T2 effective value of this T2 will be decreases. Again the effect of this particular T2 component, that network 2, their gain is increased, so that by G2 will be increased, so G1 and G2 product will be increased, so T3 will be reduced. We can minimize this other component T2 and T3 by increasing the gain of each and every component there. So noise figure generally understand the, or we can calculate with respect to the what is the system temperature. So we can minimize the receiver noise figure, okay, so by increasing the gain of the a component there. So your device, or we can say that a receiver, we can consider it highly sensitive if that noise will be reduced. So highly sensitive means what? A signal to noise ratio. Again we come to the topic. If the noise is increases, signal to noise ratio decreases. For the effective or a good receiver, that noise is to be reduced, and we need to measure the what are the various sources of noise present in the receiver there, and we need to suppress the noise by a various techniques. Here we can increase the gain of the each and every component so that we can suppress the system noise temperature, or we can suppress the effective noise temperature, so that a noise figure, whatever we can consider a figure of a merit, or we can say that a noise figure will be improved. So noise figure can be measured in terms of a, whatever the system components we are using. So if supposed to be we are consider the receiver component, suppose mixer there, and what will be the noise generated by this? So that will be reduced there. What will be the overall system noise temperature? Okay, so we can improve here. In noise, we can improve the signal to noise ratio by minimizing the which of the components we are considering. With this, we stop here.